Here's the whole idea. Take the radius of a circle and bend it around the edge. Lay exactly one radius length of arc along the circumference. The angle that arc opens up at the center is defined to be 1 radian. That's it. A radian is the angle made by one radius of arc. So the size of the angle is measured directly by arc length in radius units. And since the whole circumference is 2 pi radii long, one full turn around the circle is exactly 2 pi radians. That single fact, 2 pi radians in a full circle, is the bridge between radians and degrees. Because a full circle is 2 pi radians and also 360 degrees, half a circle gives the one equation you need. 180 degrees equals pi radians. Everything else follows from that. To go from degrees to radians, multiply by pi over 180. The other way, multiply by 180 over pi. So 90 degrees is pi over 2, 60 degrees is pi over 3, and 45 degrees is pi over 4. The exact value angles you'll use again and again. Now the first payoff. Take a sector with angle theta radians, the bold arc along the edge. How long is it? 1 radian gave an arc of 1 radius, so theta radians give theta radii. The arc length is simply r-star times theta. Watch it literally. Unroll that arc into a straight line and its length is r-theta. No pi, no fractions of 360, just r times the angle, as long as the angle is in radians. That clean simplicity is the whole reason radians exist. The second payoff is the area of that slice, the sector. Think of it as a fraction of the whole disk. The full disk has area pi r squared and it spans 2 pi radians. Our sector spans theta radians, so it's the fraction theta over 2 pi of the whole. Multiply that fraction by the full area, theta over 2 pi, times pi r squared. The pi cancels, the 2 comes down, and you're left with 1/2 r squared theta. Sector area equals 1/2 r squared theta. Again, only in radians. One more shape you'll meet. The segment, the region between a chord and the arc. It's just the sector with the triangle cut away. The sector is 1/2 r squared theta, and the triangle, 2 radii and the chord, has area 1/2 r squared sine theta. Subtract one from the other and factor out the 1/2 r squared. The segment area is 1/2 r squared times theta minus sine theta. Notice theta must be in radians for the first term, while sine theta just needs the same angle. It works out consistently. Let's use them. A sector has radius 6 and angle 0.8 radians. The arc length is r-theta, 6 times 0.8, which is 4.8. Because the angle is already in radians, we just multiply, no conversion. The sector area is 1/2 r squared theta, 1/2 times 36 times 0.8. Half of 36 is 18, times 0.8 is 14.4. 2 formulas, 2 clean answers. That's the payoff of radians. 3 traps. The big one, r-theta and 1/2 r squared theta, only work when the angle is in radians. Feed in degrees and both formulas give nonsense. So trap 2, if an angle arrives in degrees, convert it to radians first, before you touch these formulas. And 3, a segment is the sector with the triangle removed, so remember to subtract that triangle. Forgetting it is the classic segment mistake. Keep those straight, and arcs and sectors become easy marks. So a radian is just the angle you get by wrapping one radius along the circle's edge. And in those units, arc length is r-theta, and sector area is 1/2 r squared theta. Clean and simple. Just remember, those formulas demand radians, never degrees. Next, we put radians to work on the unit circle. For more, that's MarkScheme.app.